Hello again, folks. Today we're going to be doing section 10.1, which is just one of two sections from chapter 10 that we're going to be doing, and then we're basically finished. Anyhow, 10.1 is the law of sines. This is basically an array of formulas that you'll have to use as tools, basically, to solve or answer certain problems. All right. Anyhow, there'll be a diagram available to you that summarizes this information. Right? Basically, what we're discussing today is this category here, or this section of the paper, law of sines, and then the area of oblique triangles. Right? Do try to print that for reference. Right? Now, to summarize this information, let me give you a little diagram here. And the subject of trigonometry. I'm going to test out my green and see if it is legible. It's kind of okay. What is relevant to us are basically these two categories. We have to this point discussed what is referred to as right triangle trigonometry. And the formulas that are relevant exclusively for right triangles, which, as you know, have a 90-degree angle, are these. Firstly, the Pythagorean Theorem. Famously, a squared plus b squared equals c squared, or whatever labels that you choose. If you prefer, just convince yourself this is a leg squared, and the value c has to be the hypotenuse, though. Okay. These two things are interchangeable, they're basically negotiable. This is non-negotiable, that value. What is the hypotenuse? The dimension that is always across from the 90-degree angle, just to summarize. That is most important. Right? And then more recently we had discussed several trigonometric ratios. Which relate angles to the sides of a right triangle. This is a little faint. Let's see if I can get better blue. That's one, yeah, much better. And if you know SOHCAHTOA, you could basically figure this out, but just to emphasize, the sine of an angle, this is a faint black. Okay. The sine of an angle, I'll just use theta, is the opposite dimension, that is opposite of the angle, over the hypotenuse, remember, which is still across from the box. Cosine of theta, the same angle, is the adjacent dimension over the hypotenuse. Adjacent would be right next to the angle here. And lastly, tangent of the angle is the opposite over the adjacent. There are naturally many identities, as you have seen, right, and you have access to, but these are the most fundamental. Right? So we'll have those, and just bear in mind, these are relationships that pertain to right triangle trigonometry. Now, of course, there's another category, right? And the other category is what they refer to as oblique triangles. Oblique triangles are basically slanted. That's what the word means. But maybe in keeping with the definition of right, these are things that are not, do not include a right angle. at all. Okay. And there's a couple of different examples, of course. Now, basically, what's relevant for us today, all right, are these two sets of formulas. We'll be discussing the laws of sines, and then areas of oblique triangles. A little bit further down the pike, Thursday, right, we'll do the following. The laws of cosines, and then something called Hero or Heron's formula, depending upon the author. So anyhow, that's the plan for the week, all right, what you see here. And these things are section 10.1, and these things will be section 10.2. Okay? So as I mentioned before, do try to print this out, right, for reference, okay? And if you want, you could separate it like so. Formulas for 10.1 stop here. Okay. Now, let me give you a couple of examples here. Well, let me draw you another diagram to summarize some information. And I'll put it up here. I just noticed I put includes, which is not a word. Include. Good grief. Good grief, Charlie Brown. Include. They do not include right angles. They do not includes. They do not include either, or vice versa. Sorry. Oh, one other thing I want to remind you of course, too, and this is true in both cases. Triangles in general add up to 180 degrees, no matter what type of triangle. So this as a formula might be helpful. Angle 1 plus angle 2 plus angle 3 should equal 180. Okay, that is true whether you have right or if you have oblique triangles. Okay. Let's see. Here's another fun fact. Triangles, of course, have 3 angles and 3 sides. And the reason I mention that, although it is self-explanatory, is that sometimes you are asked to solve a triangle, in which case you would have to determine all 3 angles, all 3 sides. So if you see that in the instructions, it says solve a triangle, all right, and you have some of the parts given to you, all right, via the laws of sines, all right, because that's the section related material today, you could figure out what the missing dimensions are. Okay, now what would be good is to sort of examine the drawings that you are given, all right, and identify the actual types of parts that you're given. So decide whether you're given an angle, decide whether you're given a side, or any of those things in tandem. I'll erase this. here is potentially what will be given to you. Use green because it would be good if it is faint. All right. I'm going to draw three sort of generic looking triangles. And I'm going to purposely not include a little box in any of the corners because these are oblique. They do not have a 90-degree angle in them. It could be a little bit more exaggerated as you see in particular examples, specific examples, but let's start with this. Let's say that you are given one of these three situations. I'm going to highlight certain portions of this. An angle, a side, and then a second angle. Just to distinguish these angles, I'm going to put a tick mark here to generalize that this is some different value potentially from something else here. May not necessarily need to be, but I want to distinguish them for just right now. There's an abbreviation for this situation, where you have an angle, a side, and then a second angle. You might say, from the perspective of the side at least, the side is between, two angles. The abbreviation for that would be the initials basically of angles and sides. So A, S, A, right? And in a very literal sense, right, this S that is in between these two A's is referring to this drawing that you would, or the situation that you would see. Then there's potentially this situation where you have an angle and then a second angle, but the side length that is involved is not between. So to distinguish it in reference to the side specifically, the side is not between. And the abbreviation again would be the initials of those types of dimensions. So angle, angle, side, if you were to read it sort of counterclockwise. Okay. That is this last scenario, where you have an angle, a side, and then a second side. I'm just highlighting basically, as you can see. In this case, let me just say, because the angle is in the minority here, it might be best to describe it like so. Right? The angle is not between, right? As opposed to the side not between, as opposed to the side is between. This is why I'm chuckling to myself, because I have a juvenile sense of humor. If you were going to stick with the logic, all right, of, okay, we're going to use the initials. I'm sorry, I'm beaming with joy here because I'm such a stupid man. But out of politeness, we're not going to spell this the way that it actually looks. And what we're going to do is strategically just read it sort of from here, this way, all right? Because then it would be side, side, angle. That is how textbooks avoid offense, I guess you could say. All right. Anyhow, why am I bothering you with this? Because if you can identify, given one of these three situations, all right, it would be appropriate, right? Given one of these three situations, it would be appropriate to use law of sines, right, as opposed to laws of cosines, which we're reserving for the conversation on I shouldn't say we, the royal we. I am reserving for Thursday, right, because that is section 10.2. Anyhow, there'll be 2 more triangles to add, all right, to the diagram when the time comes. We're just out to master these 3, right, and these are the only types of questions that you'd be given potentially in my open math. All right, just remember, if you're given this, or this situation, it is appropriate to use the law of sines. Okay. All right, let's do a little explanation as to how this came to be. And I'll erase this. Thankfully, blue is erasing a little bit better these days. Let me draw you a simple drawing, and then I'll use green again because that seems to be to our benefit, because it is faint, right? It is just dark enough to be visible, but not distracting. Here is again a general triangle shape. The textbook that would have come with our class, right, chose to label the vertices of this triangle using Greek letters, right? A lot of times, and even on the handout that you will see, there'll be alpha, beta, and gamma, right? As opposed to capital A, capital B, capital C. Nothing wrong with that, right? But just realize that, it's an alternative. Here is, let's just call the angle here angle alpha, and I'll put it in the corner. Right? I could put the curve, the arc symbol here, but just not to mess with the inside too much, I'm going to purposely put it on the outside. Okay? I'll just label this beta, this angle, and this as gamma. The way that this works, the corresponding side are opposite, right? The angle. Alright, so if this is angle alpha, and that is something like an A, it is the Greek incarnation of A, then opposite of this would be appropriately labeled, I'll put it in a different color, A, and I'll use lowercase a. Right? The corresponding side, right, of beta would be B, and it would be opposite of this. Corresponding sides are opposite the angle. There's probably a better way to phrase that. The sides corresponding to an angle are opposite of the angles. Might be a little better phrasing. Right. Gamma, which I would have guessed is the Greek incarnation of G, just simply for its pronunciation, is opposite of what you would normally label lowercase c. Now, I would guess that the reason they didn't use capital letters is for the fact that c is so similar in lowercase, and capital form. So to make it a little bit more distinct, they went with the Greek alternative. Anyhow, let's say hypothetically that we had, now let me just, before I jump the gun here, remind you, this isn't a right triangle. Right? There is no 90-degree angle tucked in here anywhere, but we can sort of divide it. Right? If I were to strategically draw a line down the center from the vertex here to make this perpendicular to the C value here, I now have two right triangles tucked into the larger green triangle. And normally, especially in terms of areas, which we'll see later, the label that we have for this dimension is H. I don't know if that's visible on the frame yet. Looks like it's okay. What we could do, given arranging the situation so that there are right triangles there, is we could see what happens if we apply sine. Right? And you gotta remember, this is two things. I'll use a different marker. That sine as a generalization. Right? Sine of some angle is opposite over hypotenuse, according to SOHCAHTOA, right? The sine of an angle represents this fraction of the dimensions of a right triangle. If it is specific to alpha per se, the dimension that is across, opposite of the angle would be A, right? And the hypotenuse, oh, pardon me, I'm going too far. Right? The dimension in this case, opposite of H, stopped by, if you can imagine this brick wall here, is H. Right? I have to include the dimensions from this right triangle that I've created inside the green. Right? The hypotenuse, therefore, would be opposite of the box, right, which would be B in this case. Right. If I did the same thing, referring to the same side that is H side here, because there is a second right triangle tucked in here, and this is the same brick wall here, if you will, from the perspective of beta, the dimension that is immediately opposite of beta, if it hits this wall, all right, is H again. And the hypotenuse in this case is would have been A, which I erased. You would see lowercase a. Alright, now, having gone and done that, figured out what the ratio would be from the perspective of this angle, and what the ratio would be from the perspective of this angle, I ended up getting some similar features, right? Namely, the H dimension. For the sake of consistency, I'll make it the same color. It's like 3D now. That means that if I'm crafty, right, what I could do is rearrange each of these, right, so that it solves for H specifically, and then set them equal to each other. This is the kind of thing that they pull in a physics class all the time. You may have several formulas that equal the same value, the same measurement. So if you can manipulate the situation, manipulate the formulas, right, so that they solve for the same variable, then you can set the equations equal to each other. Right. Anyhow, in this case, right, it would be a matter of, to solve for H, it would be to move B. So if I do the opposite of dividing by B, it would be times B here and times B here. And it would cancel like so. So the dimension that is B times the sine of alpha would be equal to H in this respect. Similarly, right, if I wanted to solve for H, in this case, it would be a matter of instead of dividing by A, it would be times A. And then do the same thing to both sides to make it legal. The A's would cancel, and then h in this case, would be equal to a times the sine of beta. And if I take it one step further, acknowledging that these are the same, one would arrive at this, that b times the sine of alpha, it's a little faint, is equal to a times the sine of beta. I need the space, so I'm going to erase a little bit. I'll erase over here. There's one more thing, well, technically two things you can do. You could do it in one step, you can do it in two steps. If you want this to be something like an equation that is practical, right? And you think about when you were a kid and you first learned fractions, like maybe 4th grade, something like that. Eventually they brought up the subject of proportions. Here's a little thought cloud, if you will. It's fading. Remember proportions. What is a proportion? Right? A proportion is basically a fraction set equal to a fraction. Right? So if it's a fraction, that means that it has a top and a bottom. And the second fraction similarly has a top and a bottom. But more importantly, it's an equation. Right? We have all the parts here to basically create something like that. And the advantage to having a proportions equation is that we have a very simple technique in order to utilize it. Right? Basically, to solve a proportions equation involves cross multiplying. A little caveat is that you need 3 out of 4 parts. Right? If there's 4 distinct pieces in a proportion, top and the top and the bottom and the bottom, the numerator, the denominator, the denominator, you would need the 3 out of the total 4. Right? That's the way algebra works, right? As long as you have the majority of information, and you may in certain problems, then you could figure out what the missing chunk is. Right? That's basically what's going to happen here. If you wanted to make this emulate the shape of a fraction, i.e. a ratio, sitting on top, sitting next to a second ratio as part of an equation, one ratio set equal to a second, then you just have to manipulate the junk here. Right? In other words, move this b over there, move the a simultaneously over here. How would you justify doing that in either case? Well, if you wanted to move b from here to the opposite side, it would entail performing the opposite operation. The opposite of multiplying by b would be dividing by b. And if you did it here, they cancel. And if you put it here, it stays there. All right. Simultaneously, only for the reason that I'm running out of board space here. If I wanted to manipulate the situation to move a as well over to the thing it is more akin to, this is a lowercase a, this is an alpha, Greek a, if you will. I would justify doing that by performing opposite operations. The opposite of multiplying by a is to divide by a. So that would cancel here, and it would be left here. What is left over is this. A little more ferocious. What is left over is basically this. I'm going to clean it up in a minute. And I'm going to get rid of that blue because it stinks. Right. That the sine of an angle over the corresponding side, that is, I should say, the side that is relevant to it, related, is equal to the sine of some other angle, let's call it beta in this case, over its related side. That's one of basically 3 ratios that are feasible, right? If we manipulated the situation in a similar fashion, all right, what we could have gotten was yet a third ratio. We would get specifically this. The sign, if I'm happening to use gamma here, it would be gamma over c, right? Again, not to, berate the book too much. In most textbooks, they would use a capital C as opposed to a gamma. But whatever. Right? Anyhow, that's referring to this angle. Right? You would have to chop up the triangle a little bit differently if you're going to continue to use the same arrangement. Right? But it would be the same idea, the same premise of, okay, I'm going to force a right triangle in here somehow. Right? And then, look at the corresponding, the related sides, right? And apply signs to the trig ratios to that situation. Anyhow, this is collectively referred to as the law of sines. That the ratio of an angle to its related side dimension, right, is equal to the ratio of a different angle and its related side dimension. Now, if you again we're aiming at making this simulate the proportions equation, because then we can apply a cross multiplication technique to solve for one of the four pieces, right? Then you're either going to rig up an equation that entails these two, and that's usually sufficient because you could just change the labels at will. Or you're going to use an equation that rigs together these two. Right? Or in theory, this one and this one. Right? The bottom line is that you need two trig ratios, right? That are the angle, the sine of the angle over a dimension that is a relevant side dimension. Okay? And it's a very powerful technique, and it's not too difficult to remember, at least if we had the labels, in a sort of intuitive fashion. It's A and A, it's B and B. It's really C and C, right? And we're just calling it gamma in this textbook. Right? So there's an easy way to remember it. If it's the law of sines, it has to have sine in it, right? If you want to remember what the variables technically are, it would be the A's together, the B's together. That's kind of the reason why this was manipulated as such before as well. Okay. Now let's do a couple of examples. All right. And I'll give you sort of a procedure for approaching a problem. Blue is stubborn. Okay. All right. Let's start with a drawing again. Here's an example. Again, I prefer to draw my triangles in green just because I think it is easier to make it work. Is again, it's supposed to be a sort of generic non-right triangles, an oblique triangle like so. Okay. Let's say that you're given nothing more than the picture and a couple of dimensions thrown into it, right? Not all of them, but just maybe 3 pieces. Right. So what's given to you, I'll put it in blue. Let us say that you have an angle written here, and it's understood as being 50 degrees. Right? And then a second angle here, which is 30 degrees. And a side dimension here, which is labeled 10, and that's it. Okay. Now again, in the long run, if you were trying to decide between, is it the law of sines or cosines, let's examine what exactly the pieces are. Right? You got an angle, and a side. You got three things, as you will often. The side is not between the two angles, right? This, as previously mentioned, is one of our three scenarios. I always draw these things myself, but I'm just sort of pull back the curtain here. Right. You have basically this situation, an angle, and a side. So if you identify that that is what's given to you, then you could certify, yeah, I'm definitely going to use law of sines, right, and not anything else. Right? So it's okay to use. Right? Now what I would do is label them. Right? Label the angles with capital letters at least, and label the side dimensions with lowercase letters. Right? Caps, right, are angles, and let's say lowercase is side dimensions. So what I have here is an angle and a dimension that is immediately opposite of it. All right. So I'll call this A. I like capitals, forgive me. Capital A, and I'll call this lowercase a, and we'll say that it's 10. All right. Then we have an angle here, which again I'll just sort of stick with the logic of A, B, C, you know, alphabetical order. Capital B, all right, and then opposite of that there is no dimension. So what I would do is, and I'll put it in black. All right. I'm going to label it B, but I don't know what it really is yet. All right. Exhausting my sort of system of nomenclature here. A, B, there's only one corner left. So let's call this C, which is not known, so I'll use a different color here, capital C. And then notice that again, what is opposite of it? Another unknown. Okay. Now, oftentimes they just give you a picture and they say, here, have at it, you know. But let's be a little bit more verbal, you know. If they ask you again to solve, right, this triangle, what is implied by that is that you have to figure out, determine what the three angles are, either by looking at the drawing or performing some calculation, and figure out what the three sides are for this in the same manner. Look at the drawing or calculate. So I'll put a little table over here. We have sides and we have angles to figure out. Faint. Well, we have decided to label this because I started labeling the angles first. So I know that angle A is apparently 50. And that would force this to be side A, and that was explained as being 10 units, whatever it is. Right. B was also given, but it wasn't labeled. I'm just deciding to call it that. That's 30 degrees. That dimension is not known. So we will figure that out. And then last thing is C, the angle, and its dimension respectively, its side dimension. So we don't know what C is either, and we don't know what the angle is. Right. Without using anything fancy, and arguably the law of sines is fancy because we haven't done it too much. It's still exotic. you could just resort to using older formulas to figure out what the dimension here is, what the angle is here. In that instance, as long as you have two angles, right, given two angles, right, we could figure out what C is, right? How so? A triangle is automatically 180 degrees, right? And if it's a triangle, by definition, it has to have three angles, as mentioned previously. We know two of the three, therefore we have the majority of information. So if we substitute it, let's just call this angle A, B, and C respectively. Then if this is 50 and this is 30, we know their sum, and then we can figure out what C is, right, via algebra. So, what's 50 plus 30? 80, naturally. And this is equal to 180. So performing a little one-step equation, subtract 80, we can infer that angle C would have to be the balance of 100. So we got 100 degrees. Okay. 100 plus 30 is 130, 130 plus 50 is 180, everything is copacetic. And you could fill in the drawing if you want. Right. 100 degrees is what it would have to be if this is 50 and that's 30. Okay, now as for the dimensions, I need the space, so I'm going to erase this. We can figure out what B is by using law of sines. Now again, what I would do is maybe start with writing out the law of sines. The ratio is set equal to the ratio is set equal to the ratio, and then circle the two that you're going to use. So if you had the sine of A over A is equal to the sine of B over B, and the sine of C over C. What do we have? We have A, and we have A's dimension, so we're definitely going to use this ratio. We just need a second one. As long as I have 3 out of 4 parts, right, and I already have 2, that means that as long as I have 1 out of the 2 that are remaining in my second ratio, then I should go with that choice. So if B happens to coincidentally include the angle 30, and that's the thing that's missing, I'm going to use these two things in tandem, right? I'll come back and maybe use this later, right, if I need to. So let's do that. We have our simple proportion equation, and we'll substitute the appropriate values. Angle A is 50. Angle B is apparently 30. Side A is 10, and side B is mysterious. So we don't know what that is. But we have a technique. We're going to cross multiply. To cross multiply is to multiply diagonally this way, write it on the next line. Cross multiply this way, write it next to whatever you've written, wherever you've written something. And then we can rearrange the parts to figure out what the missing side length is. I'm sorry, it's a little bit faint here, but just judging from my camera, but I'll rewrite it in a darker color. And I'll put it just above here. Now, it doesn't matter which way that you start diagonally, you know. If I associate these two things, it would be via multiplication. So you'll see it as 10 times the sine of 30 degrees. We're writing an equation, so I'm going to put an equal sign. And then on the opposite side, these two things together. Just to conform to good etiquette, I'm going to put the coefficient in front. Doesn't have to be, but I think it would look nicer. B times the sine of 50. And now lastly, if you want to solve for b, because it's the one chunk that's missing out of the whole equation, then perform the opposite operation. The opposite of multiplying by the sine of 50 is to divide by the sine of 50. And as you know, right, if you can get away with murder in math. If I've done that here, doing it here is what makes it legal. There's a cancellation effect by design, and then this is basically what you will type into your calculator. Just make sure that your calculator is in degree mode before you do that. And I'll show you. Okay. So you have your calculator handy, and you, if you want, you could use parentheses, but you might be able to get away with not doing that. So if you have 10 times the sine of 30, is that divided by the sine of 50. I should set a better example and very anal retentively encapsulate things with parentheses, but I know it's going to work from experience. Okay, now you have this decimal. The decimal is 6.5 or whatever it is into infinity, right? Or at least up to the edge of the screen. All right. Let us say that you round it to the tenths place. I mean, usually they'll specify in the instructions that they want it to the tenths, the hundredths, the whole number, whatever. Anyhow, this would reasonably be about 6.5. So to add to our list here, we now have this. B is this is supposed to be crazy eyes. Okay, 6.5. I'm going to put just a squiggle equals here because it is an approximate. All right. Now, if you wanted to, you could employ this in pursuit of the next dimension. I would not do that. All right. Only because realize what you did, all right? I rounded, all right? So although you're gonna get probably an answer that anyone would go, yeah, that's fine, all right? Better to use something that is not a rounded number, right? Because we've chopped off infinity. We're going to mess with the end result a little too much, all right? For lack of a better phrase. So what I'm gonna do now is just write a similar proportion equation basically, but I'm gonna not use that dimension because I really don't need to. It's not that I'm stuck using it. I'm just gonna say, yeah, that's good, but I don't want to put this into the formula again because then I'm using a rounded number and that's not gonna make it more accurate than it can be. I'll make it slightly less precise. All right. I should say, I'll make it less exact. All right. Or not exact. Less accurate. All right. All right. So, we have this information. Now we just have this last dimension to acquire. So I'm going to start once again with the formula. The sine of alpha, A, capital A is what I went with, over A, lowercase, is equal to the sine of capital C over lowercase c. Right? Again, you could use sine of beta here and the dimension for B that we just acquired, but it would make your answer a little fishy, right? So, as long as you don't have to do that, start fresh. Right? The sine of 50 degrees would go here, and the sine of 100, which you might argue is like, hey buddy, you figured that out from the formula as well. That's true, but I didn't have to round anything. Right? I just basically subtracted. It was choose, it's absolutely correct. You know, if this is 50 and that's 30, that has no choice. That's got to be exactly 100. Okay. Now A is 10, and C is what we're looking for. So, if C is what we're looking for, same procedure, doesn't matter which way you start. You're going to multiply these two things, and I'm just going to conform to good etiquette and put the C in the front. And then multiply these two things, and I got 10 times C to 100. And then I'm just going to divide by the sign of 50 here to cancel, and divide by 50 here to manipulate. C is going to be probably something rounded again. So let's do that. All right. 10 times the sine of 100 divided by sine of 50. All right, type that and see what you get. Another decimal, 12.855, whatever it is. So for the sake of consistency, if I rounded this to a B value to tenths place, let me do the same thing. I'm going to round 12.9. Right, would be appropriate. If it's 85, right, it's about equal to 12.9. Okay, now one could say this is truly solved because we have solved for all of the angles that are possible in a triangle. There's only 3, all right, and the 3 side dimensions. So finished. Let me do another one, and then I'll show you areas. My neighbor is mowing. Yes. Here again, suppose you were asked to solve this. Same thing again. Another sort of generic looking triangle. And what you are given are these dimensions. 85. Is that visible? Looks like it is. 12 across from it. And 9. Okay. Let us again, just as a good habit, right? Make sure that it is appropriate to use law of sines, right? Based upon these dimensions. What do you have? You have just a highlight here. It's not visible. You have, that's a little bit better, a side. You have apparently a second side, and then you have an angle. And this is the funny one, right? Because it's the, I'm such a jerk, I'm sorry. Right? The very juvenile sense of humor math people, you know, like, out of politeness, it's just not spelled backwards, is what I'm alluding to. Anyhow, waka. That's what I think of this trigonometry. Snap, throw a book away. Okay. Anyhow, so yeah, this is one of our 3 choices, right? Just for reference, you know, we have, that's the last of 3. We have angle, side, angle, angle, side, and then we have the one that is actually going on here. So it is appropriate to use law of sines. Better that you laugh, all right, even if it is a cheesy joke, with little explanation, because you are more inclined to remember it then, you know. I'm not above that, you know. Cheap jokes. Okay. All right. So. What we should do immediately after going, okay, this is the course of action that I'm going to choose. I'm definitely going to use either the sine of alpha over A in tandem with the sine of beta over B and the sine of C over C. These are the laws of sines. The law of sines. These ratios are all equal. And I just need to choose two. What I'll do is strategically label the triangle. So that's to my benefit. Right? Let's maybe call this A over here just for convenience, which means I'll put an 85 in there. And the dimension across from it here is 12. And then the second dimension I have, which I'll just call B, and it is 9. And that would make this B that I would solve for. Okay. So just again to compile a list to keep track, you know, I need to know A, B, and C, and I need these sides. These are angles in order to qualify as having solved completely. Okay. We have, according to the labels that I have just arbitrarily decided, we have A. So 85 is accounted for. It's a little faint. Better. And we have 12, because that corresponds to that. And 9 is because I designated it as such. Therefore, I don't know what B is yet. I don't know what C is yet, or that dimension. I do have half of the information out of the total 6 parts. And in the case of this particular chunk of law of sines, which is sufficient, I have the majority of information. I have 3 out of 4 parts, so good. All right. Now I'm going to cross multiply this way, and I'm going to write it as sine 9 sine of 85 is equal to 12 sine of the mysterious angle, and little tricks. If I want to get a solve for B, I have to attempt to isolate the B. Now, it will be in 2 parts that I will do this. First, I'll move the coefficient of 12 by dividing here and here. All right. And what I will be left with at that point is this. Right. From the perspective of B, all right, and this is part of the sine, I have 9/12 times the sine of 85 to make it a little bit more formalized and not so faint and specific. And you could reduce the fraction to, I believe it is 3/4, right? Or put it as a decimal 0.75, it's equivalent. But we're confronted with the situation that we have historically been confronted with, it, which is that we're not trying to find a side dimension here. We're basically trying to find the argument, all right? The actual angle is what we're looking for in this case. So how do we do that? We need the inverse. Use the inverse. That means that what you would basically enter using your calculator would be this. that B, exposed to the open air now, is equivalent to the inverse sign, which is abbreviated as sine with a sort of a superscript -1. And then the contents of the inverse is all this stuff. So you could type 0.75 just because it's 9/12. Right? Or you could enter the fraction, it doesn't matter. Sine of 85. Just be careful about the parentheses and make sure that you use an inverse function for sine. Right. So in this case, just to get it rolling here, the inverse sine of, I'm going to be fancy and put things in the style of a fraction, times the sine of 85. Now, we'll also make sure that your calculator is in degree mode. This is the very anal retentive way that I have written it. Okay. Inverse sine, and then I put this in a fraction form. It doesn't have to be. You could put 0.75. All right, enter. And there's your angle. 48.3 if you round it to the 10th place. So I will say, to fill this in here, this is approximately 48.3 degrees. Now this situation is going to be a little different from the last time. If I'm going to figure out what the angle is now, for C, right, probably the easiest thing to do is to add these and then subtract from 180. So I'll erase this and slowly but surely figure this out. So if we have a triangle is equal to 180 degrees, and this is the sum of angle A plus the sum of A plus B plus C, and we know the majority of information here, that is the sum of these two things, is really 85 plus now 48.3. Unfortunately, I have no choice. If I go this route, I have to use the rounded number now. Okay. And what is that? 85 and 48. 133.3. And if I want to justify moving it for the sake of solving for angle C, I would have to do the opposite of adding, just subtracting 133.3 degrees. And then what are you left with? 10, 9, 7, 6, 4. 46.7. So the angle here, and I'm going to use a squiggle equals again because I'm using a rounded number. This is approximately 46.7 degrees. Just to be consistent here, this is about equal to 46.7 degrees. Now let me go back and finish the C dimension. Again, do be careful, or shall I say, be judicious when you're choosing which measurements to put into this formula, because ideally you want the best answer, not just something that happens to work. If I could afford not having to use a rounded number, I would. And I'm going to go with basically this incarnation of the law of sines. And fill in a little that I do know, right? A was given as 85, and the A dimension, that is the side dimension, is 12. C we just calculated as 46.7, rounded. I'm stuck with it, at least if I'm using a law of sines. And now I'm looking for C. So if I now perform cross multiplication techniques, in this diagonal I have C, this is fading out. See if this is any better. No, okay. C times the sine of 85 is equal to 12 times the sine of 46.7. If you want to be very precise, you could, if you want to store the dimensions that we had calculated before, this rounded 48.3, in your calculator. You get something that is still not exact, but it's still pretty close. And then I'm going to divide by sine of 85 here, and the sine of 85 here. Degrees, right? And basically you're going to type this, right? And that will tell you what C is. So to verify really quickly, 12 times the sine of the unfortunate 46.7 degree angle, speak so disparagingly of it, over the sine of 85. Right, should get this 8.7, looks like sixes, yep, sixes. So again, to be consistent, about 8.8. 8.8 units, whatever it is. This is done. We have coverable bases, and there happens to be 6 bases in this game. It's a weird form of baseball, you might say, right? The other thing is the area. Let me remind you of some things regarding that. Couple of things to remember. Area of the triangle is this formula historically. Base times height divided by 2, in its most concise, crunched down incarnation of itself. Right? And if you've ever wondered, I'm sure you could figure it out. All right, how did they come up with this? Area of a regular rectangle is the dimensions this way times the dimensions this way, right? So I should have done something a little bit less square here. Assuming that a rectangle has different side lengths, they don't label it as side by side. They call it length and width respectively. Just to sort of imply that the number here is not the number here. They use different words, right? And usually when you're calculating an area, it's the amount of surface on the inside of this bounded polygon here, rectangle. Now the thing is, the area formula is abbreviated L and W for a rectangle, right? But if they wanted to, they could change the labels. Instead of calling this a length, they could call this a bottom or a base, in which case the abbreviation would be a B. Would be a B. All right. Instead of calling this width, this is my aunt that always says hello to me. You're gonna crawl on my board. Dude, I don't want you to get hurt. Shoo. Come on. Yeah, go over there. There's an ant who wants to learn geometry. Anyhow, instead of calling this a width, this might be called a height, all right, or an altitude if you like, how tall it is, all right, and a logical letter would be h, right? When if you've ever seen parallelograms, right, usually that's the labeling instead, just to make it distinct from the area formula for a rectangle. They will make the area formula for a parallelogram, which is just a rectangle cropped one way. They'll use B's and H's instead. Anyhow, where am I going with this? What is a triangle really but just half of one of these things? All right? That's where the 2, of course, comes from. All right? And that's where the dimensions B and H come from. All right? Now, there's 3 different types of triangles. Right? There's these type, of course. There's right triangles, as we well know. Right, because they have a right angle. And then there's more the generic looking triangle like this, right? Which might be called acute if you're referring to it according to its angles. All right. If I'm labeling triangles according to their angles somehow, right would be the first type. Acute would be something like this, which just means that the angles are less than 90, all of them. And then there's another weird type, right, that looks like this, which is referred to as obtuse. Again, if I'm sticking with referring to triangles according to their angle dimensions. If you have an angle that's greater than 90, as opposed to angles that are acute, which are angles less than 90, and this is exactly equal to 90. Anyhow, the only reason I'm mentioning this is because if you were going to calculate an area, you need to know where to look for the dimensions, B and H respectively. In the case of a right triangle, it's really easy. It's just how tall this is the H, and how wide it is down here on the bottom is the base, right? But when you're trying to read these 2 type, it's a little bit more tricky because you have to basically look for a 90-degree angle that isn't there. Now in this case, notice how 90-degree angles are drawn. They're drawn perpendicular like this because that's what they naturally are, right? If I were to draw a sort of little wall here on the inside, to me it always looks like a brick wall because I use red a lot, and I put a 90-degree angle in here, then this dimension would be the height, right? How tall this is. And then what is exactly perpendicular to it would be the base appropriately. In the case of this type of triangle, the obtuse type, you would have to do the same thing, but the dimensions that you look for reading the height are somewhat ironically on the outside. So this would be the height of the triangle, and the base would not be here. It would not run along the bottom, right? It would start, I'm going to put dots here just to kind of bound where you should look. The base dimension would be from here to here in that instance, okay? Now you might wonder, well, why is it outside of this? If a triangle that is a right triangle comes from cutting a rectangle in half, and that again is why there is a divide by 2 here. A triangle that comes from a full-size parallelogram, all right, would have that as a height dimension, all right, instead. Basically, obtuse triangles are parallelograms cut in half, right? And what is a parallelogram? It's just another 4-sided shape. It's just a rectangle crooked one day, cropped one way. It's drunk, all right? Okay, now, where does that leave us? Well, here is how we're going to arrive at basically the area formulas for oblique triangles. This is the area formula I already wrote it, right? This is the area formula, given normal situation. All right, what if we wanted to calculate an area, but we have limited information, something less than the side dimensions, right? Let's say that you had an angle thrown into it. Then you would use this area formula. All right. Area formulas oblique triangles, right, which is going to be given to you again, but just to kind of give you an idea of how they came about. All right, this is the areas of oblique triangles and what these dimensions actually relate to, what they mean. Okay, if I had again a generic sort of looking triangle here, and maybe I have it labeled like this again, capital A, capital B, doesn't have to be that way, and capital C, then the dimension across from each of these would be the lowercase side dimensions. Capital letters are for angles, lowercase is for side dimensions. This would be C, and this would be B as in bottom. That's kind of on purpose, really. That's the reason strategically why this B is here, right? It doesn't have to be, it could have been there instead, but the orientation is to our advantage to have the B here. It's something that we could relate to, you know. Right triangle, you wouldn't bother doing this because you wouldn't need to. These other two examples, this one most obviously would be the formulas you're about to see. All right, now to complete this thought, all right, again, we would need to know a height dimension. So I could cut this down the middle here from the corner. And that's a 90-degree angle because the height would always have to be perpendicular. This is erasing itself. The height dimension, H, is that legible? Looks like it is. It's like a little chair. The height dimension is always perpendicular to the base dimension. All right. Now, based upon what we know about trigonometric ratios, we can figure out a formula using the traditional formula, but also incorporating an angle at the same time. That's really the difference here. There's going to be an angle in the formula. That's the key difference. All right. Anyhow, suppose we went through this process, right? The sine of A, an angle in general, right, is normally theta, right? Opposite over hypotenuse. I really would have to put this little dashed line in here. Yes, I want it for the height reason, but because I needed to conform to the right triangle trigonometry as a basis, right? Anyway, opposite of A would be H, right? Rather than going all the way across. So H, right? And the hypotenuse in this context is labeled C. So this is H over C, right? Again, if you want to basically fill in for the height, right, what you would need to do is basically manipulate this to solve for H, right? How do you do that? You know. I know you know. Move C, right? Times C times C. That means that H is equal to the C dimension times the sine of the angle. Right? And what you will notice as you examine that list of 3 options for the areas of oblique triangles is that all they have done really is substitute H with something that incorporates an angle. So in the case of one example that involves angle A, right, the angle over here specifically, it's still the area, oh hand, how are you, times 1/2, is, instead of writing 2 underneath, they put, you know, a half up in front, times B, and in place of what would normally be H, is a little thought cloud, you know, like this relationship. C times the sine of A. Okay. If you want to, if you wanted to do the same, go through the same sort of thought process, train of thought, all right, you could, and you would arrive at the other ones, right? The other dimensions, that is, dimensions that incorporate the other angles, not just angle A only, but angle B and angle C respectively. Just notice what happens to the formula's dimensions as a result of that. If you have the one that involves B, then the rest of it would look like this instead. A would be the bottom in that scenario, and the angle would be B. You see? Let me just erase this to get it out of the way. And the last one, just to complete this thought, if you were going to incorporate the C angle somehow, this is the way the math would work out. You would have the B value as a coefficient here, and A as a coefficient here in place of what would normally be the base. All right? It's unfortunate. I like to use this myself because at least one of those things is consistently the same. All right? It just so happens that if you wanted to use B angle, or if you wanted to use the C angle, you'd have to sort of change the orientation of the triangle that you're deriving these equations from. Not to look like a lunatic. But anyhow, you have these options, and you're going to have the resource naturally if you work in these problems. But if you want sort of a method to remind you, how, to memorize this, they're all going to involve sine, right, is the first thing. They're all going to have a half because that's what the traditional triangle formula is. The other things are basically A, B, and C, so there's some sort of alphabetical order here. And if you examine the formulas, they all have A, B, and C in them somehow, just not necessarily in order, and not necessarily all capital letters, and not necessarily all lowercase letters. But this is A, B, C, right? This is A, B, C. This is A, B, C. Okay? All right. Anyhow, do keep this table handy, right? Because you have the areas available to you. Okay? They're just using gamma in this case for the C angle. Okay. I also put these parentheses here because I wanted you to see that these are standing in for the height dimension respectively. All right? They didn't do that in the formulas that you see on this paper. All right? Good. AC there. AC and B. Okay. All right, let me give you an example of this and then I'll stop. Let's see. I'll save one of these. Here's an example. Suppose they ask you to find the area of this given triangle. Right? Again, an oblique triangle, not really right. You just sort of force the situation to be right. And that's where the formulas are derived from. Basically trying to force something that isn't a right triangle but somehow involve right triangles. Let's say that they didn't label the dimensions, but they gave you, in other words, they didn't use letters, they just used the measurement. suppose that this is 52, and this angle here is 102, and this dimension here is 90. Okay, it's not a 70, I swear it is a 90. Okay, so I don't want to just force this to conform to this, but if this is the one that you remember, right, because it is alphabetical or something alphabetical, A, B, C, then what I would do, if this is not labeled as such, is strategically do force it so that everything works out nicely. All right. Remember, the angle and the corresponding side that is related to it are always across from each other. So again, if you happen to have this formula memorized and you know that you're going to need an A to do the calculation straight, then let's just call this here A, right? Capital A. So that makes this lowercase a, right? And let's call this capital B to make this lowercase b. That means that we could stick 90 right in here and 52 right in here. And then this would logically have to be the remaining angle of 102. Right? I suppose that, you know, without, you don't even have to think that hard if you have the formula. As long as you know that these are side dimensions and this is an angle, this is the capital letter, then you probably wouldn't even need the picture. But anyhow, that's one way of thinking about it. Let's see. So to enter this nicely, you could use 1/2 in the intuitive fashion, or you could use 0.5 times 90 times. I would be anal about the rest of it. You don't really need that parentheses there, but do be careful, okay? 102. You could enter it like this, which is efficient, you know. 0.5 for 1/2 or 1/2 if you like it more stylized as such. And then sign of 102, the argument closed. Okay, and here we get this dimension. The area would be 2,288 point, let's just say 9, if you rounded it. Units, whatever it is, right? They would have to tell you that this is centimeters and centimeters, or inches and inches, or what have you. Yeah. But this would be an area approximately 2,888.9, just because I just intuitively am rounding to the 10th place. You don't have to unless they specify. Okay. If you want to be really twitty, right, just write the word units squared, right? Because in theory it's an area and all areas have to be squared. Okay. You don't know what the unit is unless I tell you. All right. And that's it. All right. Not too bad, right? All right. So on Thursday is the last class, basically the last regular class at least for the semester. So I'm going to tell you basically what I've had to decide for in terms of the final. All right. But it's going to be good. All right. I just can't say anything, you know, not to, you know, be a jerk, and I'm just kind of like, ha, hold your breath. I think you'll be happy. But just let's get through this last lesson on Thursday, 10-2, and then you will have seen everything. All right. Try to do section 10-1. I'll try to look for specific problems in my open math. All right, and that's it. I'll see you again on Thursday, rather. Okay, be well.